you have to understand the concepts from the first part in order to be able to answer stuff in the second. Like, everything builds on itself. But yeah, it's comprehensive. Like, I can't say it.
What I miss?
Huh?
What I miss?
A comprehensive exam for everything. No. No, we're stopped Wednesday, so, with material, last Wednesday with material. Just go ahead and consider it comprehensive.
Okay.
Because,
Well, what I meant more specifically is I understand it builds on itself, but is it just gonna be the latter chapters like 5, 6, and whatever we cover past this?
terminology characteristics are consistent. I keep using the same
Right.
terminologies.
I mean, if that's the case,
You're
then-
gonna have stuff that's gonna involve K-fold, you're gonna have stuff that's gonna involve linear, multilinear. I'm telling you, you get the reason why I say it's comprehensive. By the end, you'll get it, okay? I'm saying to you, prep for it to literally cover the entire course, but it will have more of a focus on the last half, okay? But the final itself will encompass your knowledge of the entirety of the topic.
Okay.
So, because we go through linear, multilinear again, as a
Okay.
result of, what's called GAMS, and we do structural with trees, and then we do bootstrap with trees again, so it's
Okay.
all repetitive, yeah.
Just one more question. Is the exam on Friday gonna be more representative of how the midterm review looks, where it's all short answer, or is it gonna be, like you
Okay,
said,
no,
more?
so structurally, giving you a whole bunch of multiple choice questions for a review would be a waste of time.
Yes.
The questions will be similar, but think about what sort of short answer questions, short answer that could be answered by multiple choice that could be asked using those questions.
Okay.
It will largely follow along the same lines. You may have to select a sentence or even a couple of sentences for a selection for an answer for a question on midterm. I typically try not to do that. Usually it's like a very short answer, a few words that fill in a statement that's maybe a couple, like at max 2 sentences. But a lot of it's going to be appropriate terminology. So as far as like matching things with your topics and definitions. But be prepared for a couple of short answers exactly like those on the midterm. The reason why is because I'm going to have at least 1 page of those, probably 4 or 5 questions, that I will sort of grade separately from the multiple choice section. So I'm going to have a multiple choice section. You'll do the multiple choice. That'll be a bulk of the exam, and then you'll probably have a page in the end where I may do 1 or 2 things. I may say, here's 6 questions, pick your favorite 4, or I might give you 4 questions that are sort of more on task oriented. So I've done both in the past. I've found advantages and disadvantages. My real problem is people don't read instructions. So I give them 6 questions, they answer all 6 poorly, I don't know which ones to give them grade for. I would rather see you, if I give you an option and I say, here's 6 questions, answer 4, do not answer all 6, because I will grade the first 4 and then you're done.
Right.
So that's how it works.
I was just wondering because it seems like some of the questions on the review could be like a paragraph or 2.
They could be.
An answer.
They could be. Yeah, they could be, and they could be that way on midterm as well.
Okay.
So, this class has to have that dialogue heavy characteristic to it to be able to describe it. Because if you think about it from this perspective, what's one of the goals of the class is to be able to have the vocabulary, the knowledge, the ability to be able to speak on the topic. Largely what I would ask you if it comes up to a short answer question and you're like, I can't exactly figure out what's going on here, tell me what you know about the topic with relationship to that. And oftentimes that will be enough for me to say, okay, I feel they've got an idea, in a direction on it.
Okay.
All right. We discussed leave without cross validation.
I have a question.
Yes.
So, is this going to be graded?
Is this another midterm?
Yes.
We'll discuss it at the end of the
Okay,
class
okay.
period. And if you guys have any further questions about the exam, I'm more than happy to answer them. But I know that that's like the only thing that's on your mind right now. So whatever I'm saying, we're going to cover new material today. you guys go, oh, no, I don't really care about that, I'm only gonna care about the old material. Yeah, we're gonna have to stick with it because you might pick something up on the way here that will help you understand what we've already done. But I will try to find a way to make sure that we use our time efficiently. I plan to have a midterm review likely on Wednesday, and then I will supplement that Wednesday's lecture and Friday's lecture that we happen to miss with material that will be supplemental to our core coursework utilizing stochastic methodology. So we're going to start talking about neural network material. So I'm going to throw that actually in here, and then when we go to feature selection, feature design, it will actually follow in chapter 6. So there's going to be a module that I'm adding actually from chapter 9 we're going to cover a little early. All right, so we've already covered most of this. So if we look at some of the characteristics of sets described or designed by the K-fold methodology, since each set is only effectively some unit minus 1 of K, right? So why is it K minus 1 of K for the training set? Because 1K is allocated to internal testing again, right? So the actual training set is designated as a unit of K minus 1 of K, and that estimate with respect to the error in the prediction will typically be biased upwards. Biased simply means that we're just pushing that threshold of error estimation up. The other word you could use here is that it will overestimate the error that can be established by this training set by applying this model methodology. Again, I think this section is trying to sort of pound into your head that more samples or more examples generally make a better model. The reasoning behind that is it's hard to pick out the perfect examples and the perfect samples from any data set, and as a result, you're going to have, for any K minus 1 training set, you're going to have a loss of information. Okay. I was talking about this to someone the other day, and they were discussing something that was interesting, and I got a good laugh at it because I thought about another problem related to it. Anybody ever seen the problem that you have whenever you're watching a compressed video on YouTube or something like that? So YouTube utilizes video compression because they can't show it to you in raw format. It's just not enough bandwidth. That video compression methodology is a systematic informational representation, right? So it tries to model what's happening on the screen, and then it tries to send you a version of that packaged modeled system and output something on it. All right. So if you guys have any idea or any constructs regarding working in data streaming or internet work, compression will matter to you at some point in time. The reason why is compression and something like, have you guys all heard of like the H series compressions like H.265 and MKV? You guys have all heard of MP3, right?
Yeah.
So MPEG layer 3 is an audio compression methodology. What it does is it takes the audio frequencies and it decomposes it into a series of subfrequencies. And then it finds patterns in those subfrequencies that can be represented as a mathematical formulation of that pattern. And then instead of storing the raw bits of the actual audio, it stores a mathematical representation of a specific model of that frequency characteristic. Okay? The same thing happens with video frames. You've got structured elements in the video frame. What happens whenever you have something like, you guys have ever seen HBO's opening? You know what it looks like? That's got that static that comes on in the beginning of it. It's like static television. I find two things funny about this. One, HBO has never been an over-air broadcast, so why would they show static to represent HBO? Because it's always been a cable service. That's dumb. But at the other side, when you think about streaming, showing something random like static, that is the worst case scenario for attempting to model it. Why would we think that? Why would something that would have random characteristics in it, random hot and cold pixels, white and black pixels, why would that be hard to compress? Why would that be hard to represent as pattern sequences? There is no pattern, all right? Noise has no pattern.
Oh.
What does the irreducible characteristics of modeling systems originate from? Noise, unpatterned things, unpatterned elements. So within every signal, within every sample, all right, so let's go ahead and do those two things together. A signal can be a sample, right? That's what you get. That's the compressed audio or compressed video. That can be your sample. So within that sample, within N, some of the information, some of the values you're getting are actually the original signal. That's the audio you want to listen to. And then some of it is interference, noise, right? It is an additive system, meaning that that noise and the sample they're together, they're in one space. It's baked into the cake, you're not getting the egg back out, all right? When I say that you need more samples in order to be able to fully understand that, what I'm saying is, if you compare multiple samples together, you'll be able to determine what elements correlate to one another. We've talked about the idea of correlation. You'll be able to tell the elements that correlate to one another versus the elements that are decorrelate, those that are not patterned. That is the noising characteristic. So the less information, right? If you've ever heard the term signal to noise ratio, SNR, in any kind of signal processing or DSP, that is what we're discussing. We're talking about I need more samples in order to be able to generalize the pattern, because if I only have a certain number of samples, I only have a certain number of the original signal, but I still have the same amount of noising characteristics. Eventually the signal and the correlation over the entire length of the vector n will overcome some of the noising characteristics with respect to that sample offset. So information-wise, we talk about this as an information gain perspective. More samples tell us more about the system in general and allow us to do what? They allow us to eliminate or to mitigate the effects of noise. Now some of you who are in the electrical space will know the answer to this. Some of you who are in more of the CS specific domains will have to really dig back in your brain in order to get back into it. But imagine that I have a sensor that has a variance characteristic of, let's do one of my favorites, ultrasonic sensors. You guys know what ultrasonic sensors are?
Yeah.
Okay. Have you ever played with them? Anybody who doesn't know what they are? Okay. What's one of the biggest problems with ultrasonic sensors? Movement. You're moving towards it. Okay? Right? So moving towards it, what happens? You actually have an adjustment to the frequency characteristic of the reflectance based upon that moving wavefront characteristic, the Doppler effect. Okay? So you actually have noise characteristics that are related to you moving forward. So if I'm using an ultrasonic sensor to detect a wall as I'm moving towards it, I'm losing some of the signal as noising characteristics from it being warped by Doppler. So that actually has this interesting impact to it where there is an uncertainty to the distance, right? So the measurement, the real measurement from the ultrasonic sensor to the wall, based upon the reflectant characteristic and the audio frequency characteristics, as well as echo within the room, can create a problem where, have you guys ever looked at the specifications for an ultrasonic sensor? It says plus or minus 3 centimeters, right?
Yeah.
Plus or minus 3 centimeters. What does that mean?
It's the range?
No, that's the variance.
That's the
Range is whatever the maximum value of the headspace needs to be, right? That's whatever can be in front of it and still get good quality reflectance. So when we talk about those values, we say plus or minus 3. What we're saying is that for every measurement, I have the real measurement, right? And then I have the estimation that is coming back from that sensor. That sensor is actually a model of the real distance. So it is y hat, that is the actual distance, right? Y hat is the approximated distance versus the real distance, y, right? So you have the real distance, the actual distance, and then you have every single sample can be either 3 greater or 3 less on average. That is going to be based upon a normal distribution, that you will have equivalence amounts that will be potentially up to 3 greater than the actual value, or down to 3 less than the actual value. So how do we correct for that problem? How do we correct for that problem? How do we try to drive that down to what is an acceptable value for us? We oversample, right? We take several samples at a given time, and we average them together. What will happen when we average them together? Since I've got an equal likelihood of being 3 over and an equal likelihood of being 3 under, that margin is actually going to get closer and closer to a central value, right? Sample enough and eventually it will be eliminated by doing what? Adding more and more samples. I keep measuring over and over and over again over time. Aggregate, what happens? If I aggregate an infinite number of samples, what am I going to get? I'm going to get the exact value. Can I ever get the exact infinite number of samples? No, I will never get an infinite number of samples. So how close can I get?
Depends on the hardware.
Well, it depends on how much memory we have to store the aggregate in. Really, that's a big consideration. But when I say that n samples end up being effectively a data set about the true characteristics of the system, then that variance, if I'm eliminating 1 over k of them in order to create a 1k local version to test my approximation on, what am I doing? I'm reducing the number of values in my aggregate by a certain amount and technically increasing the variance, the range over which that value can vary, because I'm not eliminating as much of the noise, the variance characteristics within the data frame. So I tried to find a better way to explain this. Some of you who are in the engineering space may have got better what I was going from there. I can't really come up with I've never been able to come up with a good one for computer science, because functionally, machine learning is an attempt to try to, utilizing computer systems, to better approximate real-world systems, all right? The reason why I say that is we have to have a data set. The data set is based upon what? Collections of materials and behavioral characteristics of something that is not within the computer system. We don't machine learn on things that are already in the machine. We machine learn on things that are outside of the machine. We're going back to the principal point of computing in general, and that is to give us tools to better understand the world we operate inside. So an example that I'm providing you with here, if you're ever concerned about it, all right, LiDAR and even depth focal systems have the same problem with uncertainty for stuff like self-driving vehicles. So if you ever have an interest in working on the cool edginess of autonomous robotics or self-driving vehicles, you guys all know how big that field is. If you have an interest in working in that space, understanding how variance affects the certainty characteristics of a signal coming in from some digitized source, that's what we're talking about here. But the idea of variability in the model performance as a result of reducing the information that model is learning based on, that is the consequence we're talking about once we further eliminate or further reduce K. However, we mentioned that we aren't actually concerned as much with the performance characteristics of each individual model that is trained on K minus 1 of K elements. We're interested on the average performance of the system of K-folded models. We're going to average the performance of multiple of these models together to give us what? The expected upper level of performance that can be established utilizing that version of the data set. Effectively, this is where I talk about again, what did we do to eliminate the noise with respect to the sampling characteristic, the variance of each individual model? We averaged it. We're going to take average performance here and we're going to utilize that as a system to attempt to describe or attempt to reduce variance characteristics within the model performance. Remember, this is the variance that says previously we said variance is related to model characteristics. But we said, what was the big focus on variance? It was the difference between testing and training, right? We said, oh, it's variable, it has a variable effect if it's a difference between testing and training. Now we have two different training sets. Now we're gonna say that one training set versus another training set appears to have a different degree of prediction capacity, right, accuracy, from model to model. That's interesting. We can technically treat it, those two models, as different versions of the same data set, right? They are versions of the same data set because one person gets looped in and the other person gets looped out, and vice versa, right? Everybody gets swapped in and out for the k-folds, all right? So we have a fold of 10 system, and then we go to the next version, we have a fold of 10 system. We have an overlap between fold of 10 system between step 1 and step 2 of, we had this 90%, right, in the first one. Then we shifted over and brought this one in as the testing set. So now we have this one as a testing set in the next case. We have an 80% overlap from one fold to the next, guaranteed. But we're still getting a different model. So while we have an 80% overlap from model to model in a k-fold of 10, we're still going to get a slightly different model. And what we're looking at from there is we're saying the model does what? The model fits to the data. So if the model is fitting to the data, it's learning as much about the composition of the model is the consequence of the data itself. I want to make that clear, because that's one of those weird things where there is a degree of uncertainty about that within the field right now. This is going to get heady for a second. When you have something like ChatGPT, all right, and I know it seems like acres away from where we're at, but it's not. It's not. We're describing the basic constructs that make up something like ChatGPT, right? So we're the Lego building blocks that make that monolithic structure are here in the class we've been describing. When I have something like ChatGPT, right, and I train it, it's a huge, huge hyperparametric model, meaning it has, I believe the top one is something like 13 billion parameters, right? That's a lot, like that's a chunk, okay? 7 billion is not uncommon for some of the modern GPT models, like GPT-4 is a between 7 and 9 billion parameter model, depending on if you have the vision system on it or not. The reason why I'm talking about this is I say the data creates the model, right? What would happen if you just had 7 billion randomly generated parameters? You'd have a really good noise generator, right? You start plugging in values, you start plugging in samples, what happens? The model starts to take shape. It starts to be formed by the samples that are being put through it. It gets pathways, it gets shapes, it gets discriminant boundaries. It starts developing relationships between the items inside of it. In some respects, even models as large as ChatGPT and as functionally integrated as those kind of system models are still effectively products of the data sets they're trained on. They will never be able to exceed those data sets, and they only can generate material that's based upon those sets. Go outside of it, and what happens? It says, I don't have that domain knowledge, right? I can guess, and that's oftentimes the reason why your GPT models get things wrong, is because they're guessing, they're going outside of their domain. The reason behind this is we don't actually have enough samples in the world yet to train something to be 100% accurate based upon full informational theory perspectives. And since even advanced models like GPT still require a certain amount of information in order to be able to be trained to a certain degree of accuracy, they're going to be biased by characteristics within the sets that they're working within. All right, so I know this, like I said, I went outside the scope of this from a principal perspective, but I wanted to talk about those things because they do affect what we're working on later on. So let's look at the idea of utilizing cross-validation for classification problems. Let's just throw this example back in. And rather than MSE, we're just going to utilize an ERR metric. We're just going to say ERR is related to what? ERR is the summation with respect to samples of K for I samples, right? It says, for every I sample that is a member of K, I'm going to check and make sure, right, the identity matrix characteristic of each sample Y versus the inference Y hat with respect to the number of samples that are in the set. Simple enough. So ERR with respect to K-fold is K summations of from 1 to K of N of K, again, what is that? Number of samples that are in the class K over all samples N, and that is the relative error with respect to that sample versus all samples in the set. Collectively, K-fold's system works for error rates, once again here is what? Purely binarized. It is ones or zeros. You either got it right or you got it wrong, okay? You're either on the diagonal matrix of TF, TP, right? Or you're off diagonal matrix and FNTP, right? Or FNFP, excuse me, FNFP. The ratio there becomes what we would consider as the computational accuracy of the model. As we said beforehand, it's flattened, it's two-dimensionalized, it's binary as a summation of binary averaged out over the sample number, all right? This number, the actual CD error rate, does not have to come back as a pure binary because of what? It's binary, but it is multiplied by the ratio of N of K over N. So each individual fold of K for the system is summated for each error with respect to each class. So each class will get error, all the errors will be aggregated together relative to all the samples you attempted to test against. That is the global accuracy of the system. If I want to work with something like standard error estimation or standard deviation of the model, SD is related to what? It's related to the variance of the model, which is what? Sigma squared. So sigma squared is related to that characteristic, right? So variance, what happens? That is the overall variance of the system. Standard deviation, what? Sigma, right? So it is the square root of the standard, or of the variance in the model. So if I want sigma, if I say variance is related to the global distribution, and standard deviation is related to the square root of the global distributional characteristics, I'm going to calculate that global distribution variance, which is often utilized with relationship to that square. This is a type of square error, which will tell you the relative distance element K here from the ideal K. I know this isn't exactly mean squared error, right? But it's super close here. Because once again, it is a distance metric. It is a raw magnitude of how well the K system is for local K versus systematic K, the mean K for the system. And it is saying, do this process of take the squares of error differences for each sample K over the set size. K minus 1. We said beforehand, the reason why this is K minus 1 is because the training set size is K minus 1. So this is an establishment of the variance of the model with respect to the training set. Summate it across all K and then divide by K again. Now why am I dividing by K, not K minus 1 here? Because I'm dividing by K because now I am including the samples that are within the testing set, right? I'm taking it with respect to, this is the summation across training with respect to the performance on the whole set. That is going to be the variance with respect to that set's performance, all right? So that training set versus the full set performance, the square root of that is going to be sigma, the standard deviation of the error within that system. Okay, and it says at the bottom, this estimate is useful, right? But not valid. It's not true, all right? Let me tell you, it's not true.
I have one question. What's I?
That's the identity matrix.
Yeah, the I, yeah, that's the identity matrix, I get it.
For sample I given I, right? So this is, across this axis is the predicted value, across this axis is what? The
The
actual value, right? So when I say identity, what's the identity of an identity, or what is an identity matrix? It is a matrix upon which the diagonal is 1 and all other values are 0. So it is going to be the summation of the diagonal. That's all that is indicated. An italicized capital I is an identity matrix. You guys come across that before?
Yeah.
Okay, just making sure that tracks with you. Why does it track? Why would it track? Why would the identity matrix be the appropriate one here? What about let's do this with respect to a confusion matrix. What happens to confusion matrix? Class to class, class to class, class to class, right? The correct values are going to be related to the summation of the identity.
Okay.
So how many samples are actually included within that, right? So the accuracy is included within that set. Okay. I said beforehand, and I'm just going to go ahead and leave it at this perspective because I don't want to spend a ton of time on it, but if any of you guys are real keen on looking into the reason why this is an estimate rather than a real valuation, keep this in mind. That's the reason why it's not quite right. Not quite right. I haven't included the error that is actually a consequence of testing in the error metric estimate for the K-1, which is just the training error. So I'm utilizing training error, but I'm utilizing the sample number that includes training plus testing. So effectively, I'm assuming something like the same amount of error is likely to be experienced between training and testing, or I'm predicting the amount of error that's likely to occur in testing. That would be prediction of SE, or standardized error, or SED, right? So standardized error deviation. So we say standard error with respect to CD, as this says here above, this is a hat estimate. Hat estimate. This is not the theoretical number. This is not the actual theoretical calculation of variance. This is an estimate of variance that is done numerically. Since we can't actually know the true variance of the system, why can't we know the true variance? Once again, that's the thing, is I would need all the samples in the world to know the true variance. This is just the samples variance. Samples variance. So it is close enough for us to work with, typically, but is not totally valid as a theoretical estimate of the real underlying system. Keep in mind, many times that's going to be the case for a lot of things. We talked about this one that is kind of interesting. So it says, consider a sample classifier applied to some two-class data. That's a binarized output. We start with 5,000 predictors and 50 samples. And we want to find 100 predictors that have the largest correlation with the class labels, right? Then we apply the classifier such that that we are going to utilize a logistic regression, utilizing only 100 predictors. How can we estimate that test set performance with relationship to the classifier? Well, we can use K-fold, right? That would be probably a really good methodology. We could also utilize the standard error, right? That's that variance characteristic of the system. And we can apply, within that respect, right, step 2 characteristics with not worrying about what happened with respect to step 1, right? So just apply the 100 predictors, and I don't need to worry about the test performance with those values, right? Right? I can just utilize, step 1 is episodic. It doesn't care about step 2, right? Anybody think that might be wrong? Do I have to consider what I did in step 1 in order to be able to take consideration of step 2, right? So to apply a logistic regression to the 100 predictors out of the original 5,000, what did I do to begin with?
You picked them out of the overall set.
And what methodology did I utilize?
You kind of cherry picked.
Based upon correlation, right? I utilized the largest correlation. So I used the cross correlation calculation matrix. I just created every sample to every output system. That's R. You remember correlation coefficient R? All right, I calculate R. That is the standardization to variance calculation for effectively the classifiability of each feature, right? That's how correlated that feature is to the output. So from a classifiability standpoint, how would I utilize that calculation? What method would I utilize to determine correlation? I'm not going to draw the entire correlation coefficient out, but I will say it is approximately equal to the one thing we've been describing throughout the whole class. Do I take that into consideration with respect to the training in the second set? What knowledge did I gain here? What did I cook in to the mix? I decided which feature to use based upon this. I decided it based upon the entire quantity of the valuation. But what did I need to do that? I needed the target. By telling you which features are most important, I'm telling you something about the underlying model. If I'm using the data to determine which features are most important, I've already exposed the model to all of the data points, theoretically. We said previously, one of the most dangerous things we can do with respect to this system is to not have truly reserved values to be able to make the consideration win. So if I do this process, if I take this process into consideration, I have to apply this properly. I have to apply this in the correct order. All right, so the answer that says here, this would ignore the fact that in step one, the procedure has already seen the labels of the training set. So even though the labels of the training set are not actually commuted with the features themselves, the idea that the features themselves were selected using the labels has done what? It's actually told us what the most significant elements are. So if the most significant elements have been selected, even telling you which portions of the system are significant is revealing to you the relationship between the elements. If I said previously this is a correlation, right? If I imply a correlation, I can tell you, I say, determine from this set of factors and this set of information which elements make up the system of interactive constructs that create the output. If that has already been taken into consideration or already has been done in part one, then we're kind of stuck with that, right? It's built in. I have a slide in my supplemental that should elucidate this a little bit better. But I also want to show you the flow slide real quick because we've only got a couple of minutes. So this is where pictures come back in again. All right, so let's look here real quick. First and foremost, K-fold cross-validation is a map process model. All right, this is actually a really good way of understanding how K-fold works, because we start off with our scuffle data set. All right, so that's our framework data set that we're working with. We split it into train and testing. That's the first step of the process. We have to enable the first bifurcation. What wasn't happening in that previous example was what? I didn't do the train testing split to begin with. I based my step 2 process, the folding, right, the sample folding, on information from the whole data set. So if I make any inferences from the whole data set, I have biased the model product sets, right? Any subsequent training set is going to be contained of information that is also going to be present within the testing set. So I split it into the K folds. So the process, sequentially, this process is going to work such that I must first select a pre-allocation set and then I have to supply to the system all the relevant initial data rather than just the targets I'm interested in. So I will actually have to shuffle the data with the 5,000 features and then subset those samples from the 5,000 features only utilizing my local data. All right, that's the weird part about it. So you end up with multiple different versions of which features become significant based upon the subset that is enforced here within the localized training set. So you're going to end up with multiple different impressions of which 100 features are the best from each version of the sample, because there will be slight changes in the representational power of each of those features. If you end up with the same 100 samples every time, then you're really in a good space. But typically it's not the case. So for a K-1 fold systems training, we output models by shifting process, leave out one fold in the system. We take care of all relative transformations inside the fold. All right, this is the step I was focusing on, this blue step right here. This is a big one. All transformations. This includes things like dimensionality reduction and feature compression, right, which we'll talk about those next. But the idea is I want to select features. Remember, we had two modalities we talked about for feature selection. We had the feed forwards, feed backwards, and we had the best set selection. Okay, that was one methodology we utilized. We're going to have extensions to those tools as well, but let's just imagine that we did a feed forward selection for the first 100 best samples out, or features out of those 5,000. You take care of that within the fold. That's a transformation. Anytime a transformation takes place, anytime a dimensionality reduction or feature set extraction methodology takes place, you do it within the fold, not before you start the process. Okay? It will make the relative systems inconsistent because they will not necessarily come up with the same 100 values. But it will make the relative accuracy of the system unbiased by the selection, right? If you do it with respect to the selection, that bias, that information, that exposure to the actual training or testing set, the fact that it was not split out and handled separately, will follow you all the way through this process to the point to where you'll actually radically underestimate the total error in the system, because as the system has seen that information, right? I said previously, the model takes on the shape of its relevant container, the data set. So if I give it, one of those methodologies we're looking at right now is that the features that I select is in fact a type of modeling. Telling you what is most significant takes me looking at the data, creating correlations between it, and then handing you back some relationship between the inputs and the outputs. That in effect is a model. That is a model, right? So if I minimize that system such that I keep only the best of those, the ones that score the best on that system, I've already implied the correlation. I've already implied the relationship. So since that implied relationship will be part of the data set permanently after that point, I have utilized information outside of the scope. We were talking previously about how reducing information is bad, right? Or how it kind of cripples us some. Now we're talking about how utilizing all of the information, even when we shouldn't be, is in fact technically worse, because it does not allow us to be able to objectively compare the performance of the testing set now, because the testing set has technically already been used as part of the decision-making process for the correlational characteristics. You absolutely have to treat it like it does not exist. The testing set must be taken out and put away in a locked box in order for it to be valid for future use as a model validation tool. Okay, we'll talk more about this on Wednesday, and I will probably try to entertain some additional questions for you, but I'll probably do at least 30 minutes, if not maybe a little bit more. We'll go in a different direction on Wednesday and have some conversations, and then I might even give you guys another I have a recorded version of the review from last semester, so I may either give you that or update it, one or the other. So good luck on your studying. Work on that form. I think you asked whether it was graded, and it does say on there specifically that it will be spot reviewed. So I expect that review to be treated like an assignment.
Right.
Okay. I'm giving it to you for the purpose of having you do better, but I'm also giving you the incentive of having it be worth it.
Thank you.
I didn't want to do that and the lab at the same time. So that was too much.
Well, I appreciate it because it's, when I got it and I've been working on it since Friday, it's a lot more involved than I anticipated it would be.
It's, what is it, 5 pages?
It's 17 questions with all of them having multiple parts generally, so